November 11th, 1981, Naval Submarine Base Bangor, Washington. Hood Canal stretches cold and gray under overcast Pacific Northwest skies as USS Ohio, SSBN 726, slips away from the pier, beginning its first operational deterrent patrol. The submarine's commanding officer, Captain Gerald Gnecco, has spent 2 years preparing for this moment, training his crew of 155 officers and enlisted personnel conducting sea trials, validating systems, and ensuring every aspect of this enormously complex vessel operates with the reliability necessary for strategic nuclear deterrence. In the submarine's missile compartment, 24 Trident I C4 missiles rest in their launch tubes, each missile carrying 8 W-76 nuclear warheads with 100 kiloton yields. The mathematics are straightforward and sobering. 192 nuclear warheads, each roughly 7 times more powerful than the weapon that destroyed Hiroshima, representing the equivalent of 536 Hiroshima bombs, concentrated in a single platform that will now disappear into the Pacific Ocean for 70 days of continuous patrol. Soviet Pacific Fleet headquarters in Vladivostok, Ohio, has departed. American submarines don't leave Bangor secretly. The departure procedures, the security vessels, the restricted navigation zones all signal that a strategic submarine is beginning patrol operations. Soviet intelligence has tracked Ohio's construction, studied its capabilities, and deployed extensive resources specifically to detect and monitor American ballistic missile submarines. More than 40 Soviet attack submarines currently operate in the Pacific, tasked with anti-submarine warfare missions. 15 surface vessels equipped with advanced sonar systems patrol areas where American submarines might transit. Dozens of Tu-142 maritime patrol aircraft fly search patterns, dropping sonobuoys and listening for acoustic signatures that might reveal submarine positions. The Soviet Navy has spent billions of rubles developing anti-submarine warfare capabilities, and the Pacific Fleet has clear orders. Locate and track American strategic submarines. Track Ohio. Know where it goes? Understand its patrol patterns. Demonstrate Soviet capability to threaten American sea-based deterrent forces. For the next 70 days, Soviet forces will search continuously. They will detect nothing. Ohio will complete its patrol, maintain scheduled communications with command authority, conduct all required operations, and return to Bangor without Soviet forces ever establishing its location with any confidence. The acoustic signature that Ohio generates while operating on patrol is so reduced that Soviet attack submarines searching specifically for American strategic submarines will pass within miles without detecting anything. Soviet sonar operators listening for distinctive sounds will hear only ocean ambient noise. Soviet maritime patrol aircraft will drop sonobuoys that detect commercial shipping, whales, geological activity, and nothing that suggests an American strategic submarine is operating anywhere in their search area. Ohio might as well be invisible. And it's not alone. Multiple Ohio-class submarines will operate simultaneously on patrol once the class enters full service, creating a distributed strategic deterrent that Soviet forces cannot locate, cannot track, and therefore cannot threaten. Soviet naval planners watching this capability emerge will recognize the strategic implications. Decades of investment in anti-submarine warfare technology has produced systems that cannot reliably detect the platforms they were designed to counter. Understanding Soviet shock at Ohio-class capability requires understanding what Soviet strategic submarine forces looked like in 1981. The Typhoon-class ballistic missile submarine, designated in Project 941 Akula by Soviet designers, entered service the same year as Ohio and represented the pride of Soviet submarine engineering. The Typhoon was massive, the largest submarine ever constructed at 48,000 tons submerged displacement and 175 meters in length. The submarine's size reflected Soviet design philosophy. Build platforms with enormous internal volume to accommodate 20 R-39 RIF intercontinental ballistic missiles, each carrying 10 warheads for a total of 200 warheads per submarine. Soviet naval propaganda celebrated Typhoon as the unsinkable underwater cruiser, a strategic asset so powerful and so well protected that it guaranteed Soviet second strike capability regardless of American actions. The reality was considerably more complex. Typhoon's enormous size created inherent vulnerabilities that Soviet engineers couldn't adequately address. The submarine's pressure hull was actually 2 separate hulls side by side, surrounded by external ballast tanks and covered by an outer hull structure. This configuration provided excellent survivability against direct hits, but created substantial displacement that required powerful propulsion to maintain reasonable speed. The submarine's 2 OK-650 pressurized water reactors, each producing 190 megawatts of thermal power, drove 2 propeller shafts through reduction gearing that generated substantial machinery noise. Even at slow patrol speeds, Typhoon produced acoustic signatures that NATO Sound Surveillance System, SOSUS, hydrophones, could detect at ranges exceeding 100 nautical miles under favorable propagation conditions. Soviet doctrine attempted to mitigate Typhoon's detectability through operational procedures. Soviet strategic submarines typically operated in protected bastion areas, waters near Soviet territory, where Soviet naval forces could provide extensive anti-submarine warfare protection and deny access to hostile forces. The Sea of Okhotsk, effectively a Soviet lake surrounded by Soviet territory in the Kuril Islands, served as the primary Pacific bastion. Soviet Typhoon submarines would depart their bases under escort from multiple attack submarines and surface combatants, proceed to the bastion patrol area, and operate there under continuous protection from Soviet forces. The approach prioritized survivability through defensive measures rather than stealth through reduced acoustic signatures. The operational constraints this approach imposed were significant. Soviet strategic submarines couldn't operate freely in open ocean areas without risking detection and tracking by NATO anti-submarine warfare forces. They required substantial supporting forces to maintain security in bastion areas. Their large acoustic signatures meant they were detectable at substantial ranges by hostile submarines or maritime patrol aircraft that might penetrate the bastion defenses. Soviet planners accepted these limitations because their design philosophy prioritized other factors: internal volume for large missiles, structural strength for deep diving capability, and redundancy for survivability. Soviet submarine designers believed they were building platforms that could withstand the most adverse conditions and still launch their strategic missiles. They were probably correct about that survivability. What they couldn't solve was the detectability problem. American submarine design philosophy had evolved differently throughout the Cold War. Rather than building larger submarines with more extensive survivability features, American designers prioritized acoustic quieting above almost all other considerations. A submarine that couldn't be detected didn't need to survive direct engagement because engagement would not occur. A submarine operating silently could patrol anywhere in the world's oceans without requiring defensive bastions. A submarine with sufficiently reduced acoustic signature could evade even concentrated anti-submarine warfare efforts. This philosophy reached its ultimate expression in the Ohio-class design. Development of what would become Ohio-class began in 1974 when the United States Navy initiated the Trident submarine program. The program's goal was creating a strategic submarine that could carry larger, longer-range missiles than existing platforms, while operating with acoustic signatures reduced beyond previous generation capabilities. Electric Boat in Groton, Connecticut, and Newport News Shipbuilding in Virginia would share construction responsibilities, with Electric Boat delivering the lead ship. The design challenge was formidable: create a platform large enough to accommodate 24 Trident missiles, each substantially larger than previous submarine-launched ballistic missiles, while simultaneously reducing acoustic signature to levels approaching ambient ocean noise. The submarine that emerged from this design process measured 170 meters in length, with 18,150 tons submerged displacement, substantial size, but notably smaller than Soviet Typhoon, despite carrying equivalent strategic firepower. The difference reflected design priorities. Ohio was built for stealth, with every system optimized to minimize detectable signatures. The S-8G nuclear reactor that powered Ohio was specifically designed for quiet operation. Rather than using mechanical pumps to circulate reactor coolant at low speeds, the S-8G employed natural circulation. Hot coolant rises through the reactor core while cooler water descends, creating circulation without any moving parts that generate noise. Only at higher speeds did mechanical pumps engage, and those pumps were mounted on vibration isolation systems that prevented pump noise from transmitting through the hull to the water where it could be detected. The propulsion system represented another breakthrough in quieting technology. Previous generation submarines used conventional propellers mounted on reduction gearing that transmitted power from the turbines to the propeller shaft. This approach generated two sources of noise: gearing noise from the reduction gear mechanical operation, and cavitation noise when propeller blades moved through water at speeds where pressure drops formed vapor bubbles that subsequently collapsed with acoustic energy release. Ohio employed a pump jet propulsor, a shrouded system where the propeller was enclosed in a duct that eliminated cavitation patterns and substantially reduced acoustic signature. The pump jet configuration produced approximately 1/10 the detectable noise of conventional propeller systems at typical patrol speeds. Every machinery system aboard Ohio received similar quieting attention. Major equipment like turbines, pumps, and motors were mounted on resilient mounts, sophisticated vibration isolation systems that prevented machinery vibration from transmitting through the hull structure to the water. The approach, called rafting, essentially floated major machinery on flexible mounts that absorbed vibration before it could radiate as detectable sound. The submarine's outer hull was coated with anechoic tiles, complex materials with internal structure, specifically designed to absorb incoming sonar energy rather than reflecting it back to the source. The tiles reduced the submarine's detectability to active sonar by approximately 70% compared to uncoated hulls, making it extremely difficult for hostile forces to maintain sonar contact, even if they somehow achieved initial detection. The Trident I C-4 missile that Ohio carried represented strategic capability that matched the submarine's stealth. Each missile measured 10.4 meters in length with a range of 7,400 kilometers, allowing Ohio to hold strategic targets at risk from patrol areas covering vast expanses of ocean. The missile carried 8 W-76 warheads, each with 100 kiloton yield, deployed through a sophisticated post-boost vehicle that could target each warhead independently with accuracy approaching 450-meter circular error probable. A single Trident I missile could engage 8 separate targets across a wide geographic area with accuracy sufficient to threaten hardened military installations. A single Ohio-class submarine carried 24 such missiles, creating strategic targeting flexibility that previous generation submarines couldn't approach. The operational implications were revolutionary. Previous American strategic submarines, like the Lafayette class, carried 16 Poseidon missiles with shorter range and fewer warheads, requiring patrol areas relatively close to Soviet territory to hold strategic targets at risk. This proximity made detection more likely and limited operational flexibility. Ohio's longer-range missiles allowed patrol operations in vast ocean areas where Soviet anti-submarine warfare forces couldn't effectively search. An Ohio-class submarine operating in the Central Pacific could hold Soviet targets at risk while patrolling in waters where Soviet forces had minimal presence. An Ohio-class boat in the mid-Atlantic could target Soviet installations from areas requiring Soviet forces to transit thousands of miles just to reach the search area. The combination of extreme stealth and long-range strike capability created a strategic deterrent that Soviet forces had no effective counter for. Captain Kanekow's first patrol with Ohio validated these design concepts under operational conditions. The submarine departed. Bangor transited through areas where Soviet forces were actively searching, proceeded to patrol areas in the Pacific, conducted all required operations, including simulated missile launches, communicated regularly with command authority through extremely low frequency and very low frequency communication systems, and returned to Bangor 70 days later without ever being detected by Soviet forces, despite their extensive search efforts. Debriefings with intelligence agencies confirmed Soviet forces had no clear indication of Ohio's location throughout the patrol. Soviet maritime patrol aircraft had flown search patterns through areas where Ohio had operated, dropping sonobuoys that detected nothing. Soviet attack submarines had passed within estimated ranges of 10 to 20 miles from Ohio's position without detecting the American submarine's presence. The acoustic quieting technology that American engineers had developed worked exactly as designed under real-world operational conditions. Subsequent Ohio-class deployments reinforced this pattern. USS Michigan, SSBN 727, the second boat of the class, conducted patrol operations that demonstrated even more dramatically the capability gap between American and Soviet strategic submarines. In 1983, Michigan penetrated Soviet submarine bastions in the Sea of Okhotsk, waters that Soviet forces considered secure and extensively monitored with sonar systems, surface ships, and submarine patrols. Michigan entered these waters undetected, approached Soviet Typhoon-class submarines operating on patrol, photographed the Soviet submarines through periscope observation, collected acoustic intelligence on Soviet submarine signatures, and departed the area without being detected by Soviet defenses. The operation demonstrated that American attack submarines could penetrate Soviet most heavily defended waters to conduct intelligence operations, and by extension, that American strategic submarines operating in open ocean patrol areas were essentially invulnerable to Soviet detection efforts. Soviet Admiral Sergey Gorshkov, Commander-in-Chief of the Soviet Navy, received intelligence reports about American strategic submarine capabilities with increasing concern throughout the early 1980s. By 1984, his assessment was unambiguous. The Ohio-class program had rendered Soviet submarine detection networks obsolete. In classified discussions with Soviet defense leadership, Gorshkov acknowledged that Soviet anti-submarine warfare forces could not reliably detect or track American strategic submarines, meaning Soviet capability to threaten American sea-based deterrent forces was negligible. This assessment had profound strategic implications. Soviet military planning had always assumed that in a nuclear conflict, Soviet forces could potentially neutralize some portion of American nuclear capabilities through first strike operations, destroying land-based missiles in their silos, engaging strategic bombers before they could escape their bases, and potentially threatening some American submarines through concentrated anti-submarine warfare efforts. The Ohio-class capability eliminated that last assumption. Even in the most optimistic scenario where Soviet forces somehow neutralized all land-based missiles and strategic bombers, 18 Ohio-class submarines operating on patrol with 192 warheads each represented 3,456 nuclear warheads that Soviet forces had no ability to threaten. Those submarines guaranteed devastating American retaliation regardless of Soviet actions. The strategic stability this capability created was exactly what American nuclear doctrine intended. The concept of assured second strike capability, The guaranteed ability to retaliate even after absorbing a first strike provided the foundation for deterrence theory. If both sides knew that initiating nuclear conflict would result in their own destruction, regardless of military advantages they might achieve through surprise, then neither side would rationally initiate conflict. Ohio-class submarines provided assured second strike capability with confidence levels approaching absolute certainty. The submarines were undetectable during normal operations. They could launch their missiles from positions Soviet forces couldn't threaten. And there were enough submarines that even catastrophic losses of multiple boats wouldn't eliminate American retaliatory capability. Soviet military planners, looking at this capability, recognized they had no military solution. They couldn't develop anti-submarine warfare technology that could detect Ohio-class submarines reliably because the acoustic signatures were too reduced. They couldn't develop weapons that could threaten submarines they couldn't locate. They couldn't develop doctrine that addressed threats they couldn't counter. The technology gaps that created Ohio-class acoustic superiority reflected cumulative American advantages in multiple engineering disciplines developed over decades. Acoustic quieting for submarines required advanced materials, science, precision manufacturing, sophisticated computer modeling to predict sound propagation, and systems integration that optimized every component for minimal noise generation. American capabilities in each of these areas exceeded Soviet equivalents by significant margins. Propulsion technology provides the clearest example. The pump jet propulsor that Ohio employed required extremely precise manufacturing to achieve designed performance. The blades that moved water through the shrouded duct needed to be manufactured with dimensional tolerances measured in thousandths of millimeters to minimize flow disruption that could generate noise. The duct housing needed acoustic properties precisely calculated to absorb rather than reflect pressure waves. American manufacturing capability could meet these requirements. Soviet manufacturing struggled to achieve the precision necessary for comparable performance. Even when Soviet designers understood the theoretical requirements for pump jet propulsion, Soviet factories couldn't manufacture components to required specifications consistently. Materials, science advantages extended to every noise reduction system aboard Ohio. The anechoic tiles that coated the outer hull consisted of synthetic rubber materials with carefully designed internal structure, air pockets, density variations, and layering that absorbed incoming sonar energy across a range of frequencies. Developing these materials required understanding of acoustic physics, polymer chemistry, and manufacturing processes that could produce consistent material properties. American research institutions and chemical companies had invested decades in developing such materials. Soviet research produced anechoic coatings with some effectiveness, but Soviet materials typically absorbed 30 to 40% of incoming sonar energy, compared to American materials achieving 70% absorption. That difference meant Soviet submarines remained significantly more detectable than American equivalents, even when both employed anechoic coatings. Computer control systems provided another area where American technology advantages translated directly to acoustic quieting. Modern submarines generate substantial noise from crew activities, people moving through the boat, operating equipment, conducting normal shipboard operations. Ohio employed sophisticated monitoring systems that detected internal noise sources and provided feedback to crew members to minimize acoustic signatures during critical patrol operations. Automated systems controlled machinery operation to optimize quieting, adjusting cooling systems, managing electrical loads, coordinating pump operations to minimize cumulative noise generation. Soviet submarines relied more heavily on manual systems and procedural controls, with crew members following written procedures rather than receiving real-time feedback from automated monitoring. The approach worked, but didn't achieve the acoustic signature reductions that automated optimization provided. Reactor systems reflected perhaps the most fundamental technology gap. Ohio's S8G reactor operated with natural circulation at patrol speeds, eliminating pump noise entirely. Achieving natural circulation required precise thermal management, sophisticated coolant chemistry to ensure consistent heat transfer properties, and reactor core design that promoted efficient convective flow. Soviet naval reactor designs generally required continuous pump operation even at low speeds, and Soviet reactor pumps generated substantially more noise than American equivalents because Soviet manufacturing precision couldn't achieve the tolerances necessary for truly quiet pump operation. American reactor coolant pumps were machined to dimensional tolerances of 0.001 millimeters in critical components, ensuring that impeller rotation generated minimal vibration and hydraulic disturbance. Soviet equivalent systems were machined to tolerances of 0.05 to 0.1 millimeters, perhaps 2 orders of magnitude less precise, resulting in pumps that generated significantly more vibration and noise during operation. The cumulative effect of these advantages created acoustic signature differences that weren't incremental. They were orders of magnitude. Soviet attack submarines conducting anti-submarine warfare operations could detect Soviet Typhoon-class strategic submarines at ranges of 50 nautical miles or more under favorable acoustic propagation conditions. Those same Soviet attack submarines could detect Ohio-class submarines only at ranges under 5 nautical miles, and only under near-perfect conditions, where the Soviet submarine was positioned directly in Ohio, its path with optimal sonar geometry and favorable propagation conditions. More typically, Soviet submarines passed within 10 to 15 miles of Ohio-class boats without detecting anything at all. The American submarines were effectively invisible to Soviet sensors. By 1997, the United States Navy had commissioned 18 Ohio-class submarines that provided the backbone of American strategic deterrence. The submarines operated on 70-day patrol cycles, departing from either Naval Submarine Base Bangor in Washington or Naval Submarine Base, Kings Bay in Georgia, transiting to patrol areas in the Pacific or Atlantic, maintaining patrol operations for approximately 60 days, and returning to base for crew rotation and maintenance. At any given time, approximately 12 to 14 Ohio-class boats were either on patrol or preparing for patrol deployment, ensuring continuous at-sea deterrent presence that Soviet forces could not threaten. The submarines maintained communications through extremely low-frequency radio systems that allowed command authority to contact submarines at patrol depth without requiring them to approach the surface and potentially expose themselves to detection. The system was robust enough that Ohio-class submarines could remain completely submerged for their entire 70-day patrol while maintaining all required communications. Soviet attempts to match Ohio-class capability produced minimal results. Soviet submarine designers recognized they needed to reduce acoustic signature substantially, but achieving the necessary reductions required technological capabilities Soviet industry couldn't provide. Soviet submarines constructed in the late 1980s and early 1990s showed incremental improvements in quieting, but they never approached Ohio-class acoustic performance. The Borei-class strategic submarine that eventually replaced Typhoon incorporated some acoustic quieting features learned from studying American designs, but Borei-class boats remain approximately 5 to 10 times noisier than Ohio-class submarines, according to acoustic intelligence analysis. The gap that emerged in the early 1980s has persisted for more than 4 decades because the underlying technology advantages that created it have also persisted. Ohio-class submarines remain operational today in 2025, though 4 boats have been converted from strategic missile submarines to guided missile submarines carrying Tomahawk cruise missiles for conventional strike missions. The remaining 14 strategic submarines have been upgraded with Trident I D5 missiles that provide even greater capability than the original Trident I, ranges exceeding 12,000 kilometers with improved accuracy and more advanced warheads. The submarines receive continuous modernization, updating electronics, communication systems, and various subsystems while maintaining the acoustic signature advantages built into the original design. The United States Navy plans to operate Ohio-class boats through the 2040s while developing Columbia-class replacement submarines that will maintain similar acoustic performance with updated systems. No other nation has achieved acoustic signature levels comparable to Ohio-class submarines. Russian Borei-class boats represent Moscow's best attempt at matching American capability, incorporating pump jet propulsion and modern anechoic coatings, but acoustic intelligence suggests they remain substantially noisier than American strategic submarines. Chinese Type 094 strategic submarines show even larger acoustic signature deficits. British and French strategic submarines operate with acoustic performance approaching American levels, but those programs benefited from extensive NATO cooperation and technology sharing. The Ohio-class acoustic advantage established in the early 1980s remains an American capability that no potential adversary has successfully matched. The strategic implications continue shaping nuclear deterrence doctrine for all nuclear powers. Submarine-based nuclear deterrence provides the most survivable component of strategic nuclear forces precisely because submarines can remain undetectable during normal operations. Land-based missiles and silos have fixed locations that hostile forces can target. Strategic bombers require time to escape their bases before hostile forces can engage them. Submarines operating silently in open ocean provide assured second strike capability that no military technology can reliably threaten. The Ohio-class program demonstrated this concept so effectively that submarine-based deterrence became the foundation of American nuclear strategy, with the majority of American nuclear warheads deployed on submarines rather than land-based missiles or bombers. Soviet military planners, watching Ohio-class capability emerge in the 1980s, recognized they were witnessing a strategic shift they couldn't counter. They had invested enormous resources in anti-submarine warfare, building sophisticated sonar systems, deploying hundreds of attack submarines and maritime patrol aircraft, developing doctrine specifically designed to threaten American sea-based deterrent forces. The Ohio-class program rendered much of that investment ineffective. Soviet forces could search for American strategic submarines, deploy extensive resources attempting to track them, and achieve essentially zero success in locating submarines that were actively operating in areas Soviet forces were searching. The capability gap was something better. Tactics or more resources could address. It required fundamental technology, advantages Soviet industry couldn't provide. When Captain Neko brought Ohio back to Bangor after that first patrol in early 1982, Soviet intelligence analysts reviewing their tracking attempts realized they had detected nothing during the entire patrol. Their most sophisticated anti-submarine warfare sensors had failed to locate a submarine they knew was operating in their search area, carrying strategic weapons they knew threatened Soviet territory. Soviet naval officers received classified briefings acknowledging that American strategic submarines had become effectively undetectable with current Soviet capabilities, meaning Soviet ability to threaten American sea-based deterrent forces was negligible. The strategic balance had shifted decisively toward American advantage in the most survivable leg of nuclear deterrence. The Soviet Typhoon was a submarine built like a tank, massive, heavily armored, designed to survive under the most adverse conditions while delivering devastating firepower. Soviet designers created an impressive platform that reflected their engineering philosophy. Build strong, build big, build survivable. The Ohio class was a submarine built like a ghost, designed to vanish into the ocean, to operate undetected indefinitely, to deliver strategic capability from positions hostile forces could never threaten. American designers created a platform that reflected a different philosophy. Build stealthy, build quiet, build undetectable. When these philosophies produced submarines, and those submarines entered operational service, only one approach created assured strategic deterrence. The submarine tank could be found, tracked, and potentially threatened. The submarine ghost disappeared into ocean depths and remained invisible despite everything hostile forces deployed to find it. Soviet Typhoon was submarine tank. Ohio was submarine ghost.